let's start with this triangle here, where the hypotenuse is equal to 1, and our angle is x. So if we take the cosine of our angle, x, it'll be a over 1, which is just a. So we can replace this part here with cosine of x. And if we're taking sine of our angle, that's opposite over hypotenuse, b over 1, that would just be equal to b. So we can replace this with sine x. Now, let's extend this into a circle. So, if this was the radius of a circle, we can fill in the rest of it something like this. It's a pretty bad circle, but that's fine. And the radius of this circle is now 1. Another circle that we can make is here, where this side, cosine of x, is the radius. And that'll look something like this. And we're interested in two shapes that this roughly makes, and that is this one here, inside the original black triangle, and this one here, outside of the original black triangle. Now, we can say that the area of this original right triangle right here that we started with, it's greater than the area bound by this blue line here, but it's also smaller than the area of this whole bigger shape, including this curved area outside of the triangle. It's kind of in between those two. So we're going to end up using the sandwich theorem. But first we have to figure out some expressions for these areas. So the triangle here is not too bad. We're going to use 1/2 base times height. Our base is cosine of x. Our height is sine x. So the area of our right triangle, so I'm going to call this A of our right triangle, is equal to 1/2 cosine of x sine of x. Now let's do our area of our larger, this is a circle segment, this whole shape over here. So I'm going to call it area of our big circle. Now, the area of a circle is just pi r squared. And here our radius is of this circle segment is 1. So, the area of this big circle with a radius of 1 is just pi. The problem is it's only part of this circle, this section here. How much of it is it? Well, it's going to be our angle, x, over 2 pi. And this is in radians, of course. If you think about it where x is 2 pi, that would mean we're talking about the whole circle's area. And this would cancel out and just be 1, and we'll get our original area of the circle, pi. Let's say x was, for example, pi. That would mean we're talking about half of this circle here, the area of that, and this would become 1/2. So it does make sense in that way. Whatever x is, we're going to divide it by 2 pi, and then multiply it by pi in order to get the area of the segment within that circle. And you might notice these pi's cancel out. We're going to nicely get that the area of this bigger circular segment is x over 2. Now, one last shapes area that we have to determine, and that's the area of the small circle segment, I should add. Now, this one here, we're going to do it in a similar way. The radius, though, is the cosine of x. This distance here is now the radius of the circle. So we're going to say, for pi r squared, we have pi cosine squared of x, cosine of x squared. And again, we're going to add on that x over 2 pi because we're talking about the segment of that circle. Now, again, pi's cancel out. And we get, for our area of this smaller circle segment, x over 2 times cosine squared x. Great. Now let's move on to the squeeze theorem section. So we're going to need some room. We know that the smaller circle segment here, bound by this blue line, it has the smallest area, and that is this guy right here. So we're going to say x over 2 times cosine squared x is less than or equal to the area of this triangle here, which we found is 1/2 cosine of x sine of x, and that this triangle here has a smaller area than this bigger circular segment. So that's smaller than or equal to x over 2. Now let's multiply everything by 2 so that these all go away. We're going to get x times cosine squared of x is less than or equal to cosine of x sine x, which is less than or equal to x. And now let's divide everything by x so that these x's go away. We're going to get cosine squared of x is less than or equal to cosine of x sine x now over x is less than or equal to 1. One final thing we're going to do before taking the limit is divide everything by cosine of x. So if we divide this by cosine of x, we're just going to get 1 cosine of x. It's less than or equal to, it's going to cancel out this here, and we have our sine x over x. And here we're going to get 1 over cosine of x. Now we'll take our limit. So I'm going to write it over here. The limit as x approaches 0 of cosine of x is less than or equal to the limit as x approaches 0 of sine x over x, that's the one we're trying to figure out, is less than or equal to the limit as x approaches 0 of 1 over cosine of x. This one's not too bad. We plug in 0. We know cos of 0 equals 1 is less than or equal to this limit that we're trying to evaluate. Sine x over x is less than or equal to, and again, if we plug in, there should be a 0 here, shouldn't there? Yeah. If we plug in 0 here, cosine of 0 is just 1, 1 over 1 is 1. So, if we know that the left side of this limit, or rather the left side of this expression here is less than or equal to the limit we're trying to find, which is in of itself less than or equal to 1, we know this limit has to be equal to 1. So therefore, we can say this limit equals 1 as x approaches 0. I forgot that again. And that is the proof of this limit. Hopefully you learned something and you found it useful. Have a great day.